modeling extreme events with PyMC. So this will be a talk where I use PyMC to basically study a very explicit example, extreme rainfall in New York, actually. So bit of an intro. Last couple of years, we have seen many extreme weather events. This year, we had temperature records in Texas. We had last year historic droughts, flash floods in New York City, the one I will be focusing on like 2 years ago, and this list goes on and on. But what I found interesting is when such extreme things happen, like they say, oh, it's the worst rainfall since so many years, like how can we think as a data science think about that? Not just look in the table and see like, oh, all right, I have 50 years of data. This is the first time this happened, but how can we quantify that? And yeah, maybe make some predictions out of that. So here's the outline. So first off, statistics of extremes. It sounds maybe a bit boring, but I promise it's actually quite interesting, but I will keep it short. Just so that we can focus on the takeaway. Then, quick intro to Bayesian modeling with PyMC. It would be helpful if you already have some experience with Bayesian reasoning. We had some sprint session about that as well, but this will be a very quick recap in case you're not super familiar with it. Then the example, that's the extreme rainfall in New York, modeled with PyMC. So that will be the bulk of the talk. And then a bit as a bonus, slightly more complex example where I'm going to use Gaussian processes. Earlier this conference, I think on day one, we already had a great talk about Gaussian processes. So I'm not going to redo that. I'm just going to apply it. So let's take it from here. Statistics of extreme events. So this is the brief introduction. In the background, you actually see an extreme event. This happened in the Netherlands in 1953 when there was a water flood. And actually, that sparked a lot of interest in how you can think about that. I'm not going to talk about that particular event. So as I said, I'm going to talk about the rainfall in New York. So that actually happened like 2 years ago. Picture on the right, you see cars basically floating in on the highway, and then so after that happened, it was clear that there was a new record of rainfall that fell in a single day. So there was 8.4 inches, and then so that was the highest on record. And then how extreme is that? So natural question was, what was the previous record? So let's look at that. That was like 44 years ago of 6.7 inches. So that's significantly lower. So what happened in September was indeed extreme. And we see here basically just a plot of all the daily rainfall. So the question then is like, how extreme is this? Or actually, maybe a better question to ask is like, given a certain level, what I mean is like, say, 4 inches. So how many years do we expect it to happen? So is that maybe every 10 years? And then I can ask similar question like 6 inches. So how often do we expect that to happen? And then, well, maybe that's every 40 years and so on. Naive way to approach it is just look at all the available data and just count how often such things happen. But for the extremes, that's not going to be very precise because the 8.4 inches happens only once, but we happen to have just 50 years of data, but it doesn't really mean it happens only every 50 years. So the more precise way to do that is if you can somehow fit a probability distribution and use that to answer questions like how often something happens. So then the question is which distribution to fit. So that's where extreme value theory will come into play. So I'm going to look at the same data again as we had in the previous slide. So I'm looking on the left. But what I've done here is I highlighted per year the maxima. So each year I only take the maxima. And the rest so I have basically 1 day a year. And the rest of the data I'm going to throw away. So it's a bit radical, but it will be clear why we're doing that. So in general, for natural phenomena like rainfall, temperature data, etc., if you look at daily data, that is a complex distribution, which we don't know. But if we follow this methodology, only taking the annual maxima, we get the data look something like this. And here we can actually describe it with something called extreme value distribution. So there's actually a theory that states under which conditions you can fit that distribution, and this distribution will look something like this. And this I want to emphasize here, although I'm focusing on rainfall data, this is a very general statement. So this has been applied successfully not only to rainfall, temperature, stock market crashes. If you are working trying to predict server loads, MAC peaks, you can all, if you focus on the extremes, fit typically successfully this distribution. So this distribution has 3 parameters. The interpretation doesn't really matter too much, but you can think of them like a location, scale, and the shape, how tail something is. So the higher the xi, the more extreme things we can expect. So this distribution function we're going to use in PyMC. But before we're going to do that, as promised, quick intro into Bayesian modeling with PyMC. So let's contrast that with a non-Bayesian method. So if we take any machine learning problem, we typically want to minimize some loss function via gradient descent. So artist impression here on the right. So we try to find this global minimum here, and maybe we have taken this path. Typically, there's a very fast approach, but 2 things that are hard with this approach is we may find this minimum, but we have no good way to quantify how certain we are with our estimate. So think about how would you go about constructing a confidence interval, for instance. Or if you have some prior information, whatever that may be, it's typically not very easy to incorporate that in your standard non-Bayesian framework. So let's then look at the Bayesian framework. So super quick intro. So the Bayesian framework, all as the name suggests, focuses on Bayes' rule, which we have here in the middle of the screen. And what we are interested in is basically on the left, the so-called posterior distribution of model parameters theta. So the model parameters theta we're after, given some data x. And we can compute that using Bayes' rule. So this one here is, which is what we call our likelihood function. So that's basically given some theta, what distribution your data will follow. And we have a prior distribution. So why is this useful? Well, the uncertainty now for parameters is captured via this distribution. So another artist impression on the right. So we have, say, if theta is 2-dimensional, it may look something like this. So some complex distribution. But the width of that peak will tell you, like, yeah, how certain are you, right? So we can, so the equivalent in maybe non-Bayesian methods, we just to find only this maximum in this case. Here in the Bayesian method, we're interested in the entire distribution. So we want to capture the whole thing. And so that's going to be a bit more work, actually. And we're going to leverage PyMC to do exactly that. And then the other thing is, if we focus on Bayes' rule, there is this P of theta here, which is our prior information we have. And in our example, we'll look at 2 examples. The first case, we don't really have a good way to specify this, so we make it uninformative. But in the second example, the Gaussian processes, this one will actually become very important. So I'm not going to go into the details of how you actually sample from a distribution. That's too technical for the scope of this talk, but that's the purpose of PyMC. So, quick recap of what PyMC is. It's an open source library for probabilistic programming in Python. As we will see with some code snippets, it's a very intuitive way to code up Bayesian models. It has an effective Monte Carlo Markov chain sampling, and it has lots of built-in tools to inspect your distributions. So it basically comes with batteries included. And the PyMC community is great. If you have questions, you get typically answers real quick. So yeah, even as beginners, I think this is great to start to play around with. All right, so we captured now very quick introduction on extreme value theory, very quick introduction on Bayesian modeling and PyMC. So let's put these together. So back to the rainfall in New York City. So what we're going to do here is we're going to fit a distribution based on the rainfall data. So this is the entire PyMC program I use, except for loading the data, etc. And I think what's also missing is an import PyMC as PyM. But this is basically it. So the first line is you basically define what your model is, and then we will step through it. So here I defined prior distribution. So in case of the extreme value distribution, there were 3 parameters. So I defined distributions for each of them. And these exact values, that is more like experience, intuition, what they should be, but not super relevant for this talk, how I figured those out. But the important thing is it's very clean code. So you just have basically one line to define what the prior distribution is. Then the next thing is the likelihood function. So this is an extreme value theory distribution, which we discussed a few slides back. And what you can see here, it depends on these distributions. So this mu, sigma, and psi here you can think of them as not as a parameter, but really as a probability distribution each. So they will fit into this likelihood. And then Z here is our data. So this is basically the rainfall data. And to be more precise, this is once we took the annual maxima. So in our case, this is like 50 data points. So that's not an awful lot. And then once you set up the model, you need to sample from it. So that's this line. And so in this case takes maybe a few minutes to get sufficient samples. And then what we're after is the posterior distribution for these parameters. So this is a 3-dimensional distribution, so that's somewhat hard to visualize, but I plotted basically when I average out the other two. So I have for each of them the distribution. And as you can see, so mu, that's around 2.8, but it varies roughly between 2.6 and 3. So that tells you, like, since we had limited data, we don't really have a very precise estimate of what mu is, but by looking at the entire distribution, we basically know the uncertainty. Similar for the other two. So yeah, this is probably the most important slide of this talk. Basically, to emphasize, like, we'll go to the results in a second, but yeah, starting with base rule, a prior, a likelihood, and a posterior, only few lines of code, and then yeah, you fit the model, and then it's afterwards straightforward to compute any analytics you care about. So that's what we're going to do next. So one step back. So as I mentioned earlier, So when we want to discuss about how extreme something is, we're going to look at return levels given the return period. So what I mean by that is, say, every 100 years, we expect to observe something like, well, just let's look at this graph, say like 8.5 inches or more. Or if I look at, say, the other extreme, like 20 years. So every 20 years, we expect something of 6 inches or more. So mathematically, that's just this function. So we say the return level, and then this is what you observe. So it's something bigger than a given return level. And then the probability is basically one of the period. So the 40 years, 60 years, and so on. And what we want to do now is actually, I'm not going to do the algebra, but invert it, write this as a function of the return period, and then get the return level out so that we can construct this graph. And that's what I did with PyMC. So this is a few other lines of code. So let's step through those. So again, we specify what our model is. Here I add some data, which is our return period. So that's a whole bunch of values ranging from 10 to 100 years. And then here I basically computed the return level based on the return period as a function of these parameters, which again are distributions. So hence the output of this is also a distribution for each of the return periods. So how you can think about it is the thick blue line is basically for each return period is the mean of that distribution, and that width is basically the uncertainty. So we can read off for our example in hand. So for when we observed the 8.4 inches, that actually corresponds to an event we expect to happen every 83 years. So that's relative extreme. But as I mentioned before, there's quite some uncertainty here. But again, this is the beauty, I would say, of the Bayesian approach, is that there was no extra work needed to get these uncertainties. We get that pretty much for free because we're working with distributions all the way. If you were to do non-Bayesian method, you have to do more work to figure that out. All right, so this is the main example. So let's switch gears and look at a slightly more complex example. So we're going to go slightly faster to this, but this is more to showcase, what PyMC is capable of, and just to showcase yet another technique.
Hey, Jorn, we have about 10 minutes. Just want to give you a heads up.
Thank you. So the Gaussian process prior. So I will keep it brief. So going back to the previous model, so how can we make it better? So one naive suggestion is like add longer history, go further back in time. Well, A, that data may not necessarily be available, and B, they may not be appropriate, especially since we know the climate is changing. Looking what happened like 150 years ago is probably not super relevant for what's happening right now. So instead of adding more time, we can do something else, and we can make it a spatial problem. So if I look at the map here, so the red dot is what we have been focusing on. So data for a single weather station. But what I can do instead is look at all these stations and basically use their data as well to make better prediction for this single station. And we can do way more with that as well, which I will show as well. But for now, the focus is how can we use more stations to make a better prediction for this single red station. So the answer to that is a Gaussian process. And to be more precise, to use that as a prior, which I alluded at the beginning of the talk. One great advantage of a Bayesian approach is that you can use prior information. And here, prior information is going to be basically observations from other weather stations. So super quick intro about Gaussian processes. As I mentioned, there's already been a great talk about explaining it in detail. So I'm not going to do that. I'm just going to tell you what it is. So instead of basically, say if we have the 10 stations, have 10 individual prior distributions with parameters mu1, 2, 3, and so on corresponding to each of the stations, we're going to say, well, we make mu, we make that a function of x, where x is the location of the different stations. But mu, so this is probably the difficult part of what the Gaussian process is. Mu follows a probability distribution. So what we're basically doing is we sampling now functions. And that is somewhat illustrated here on the right. So each of these lines is a function, and we sampled that from a Gaussian process distribution. And what you will see, so the crosses, those are observations at locations x1, x2, x3, that these lines tend to go through my observations x, or at least close to it. But the further away I'm from my observations, I'm less certain. And then, as you can see, it fans out here. But if in this case, I have, say, a few observations next to each other that help you figure out what this function should be. And that's how basically via the Gaussian process prior, we can actually learn, have the different stations learn from each other. So how does that look in PyMC? Slightly more complicated, but the structure is still the same. So this is just specifying where the stations are, some constant data, some hyperparameters, not super relevant. And then these are my prior distributions, which I had before. So I have one for mu, sigma, and psi. And now I'm basically specifying that they depend on a Gaussian process, which depends on the coordinates for each of the stations. So it's maybe not super obvious from this slide, but this is now a model for my 10 stations simultaneously. But we have the same structure. So we have our 3 priors, which are now functions. And then we have a likelihood as before. And as you can see, the notation suggests that we now have the many stations. So again, we can sample from this like before. Nothing really changes. And then we can evaluate this. So I did that again for the same station. So as I said, like, again, we're going to look at, for now, only at the prediction for this single station. So the blue is what we had before, and now we have the orange. So it's slightly lower, but what's more important, actually, that the uncertainty of the orange fit is now only half of what we had before. So going back to the example of Hurricane Ida, what initially our estimation was, it was a once in an 83-year event. Now it's actually a once in a 100-year event. Now we incorporated information of nearby stations, but as I said, the uncertainty is only half. So we are more, we have better predictions this way. There is no need to focus only at one station. So this is slightly different, different code, but same ideas as before. So I ran this with 3,500 stations actually in the United States. I haven't depicted the various locations, but they're somewhat spread out. But with the Gaussian process prior, I can also make predictions for points where I have no data. So I can make this grid as fine as I want. And as you can see here, you can see here's a lot of rainfall in this area of the States. Here it is less because there's a mountain range here and so on. But this is just to illustrate that, you can make predictions for locations where you have no actual observations. As long as you have somewhat nearby observations, you should be able to make precise enough predictions. All right, so that was the slightly more complicated example. The takeaways.
Oh, sorry, real quick, just wanted to give you 4-minute warnings, and we have a couple questions in chat. So
okay, perfect. So very quick, the takeaways. If you think about modeling extreme events, doesn't have to be weather. Think about extreme value theory. If you want to do some Bayesian modeling in Python, I would consider PyMC. If you're working with spatial problems, consider a Gaussian process. So that was the talk. Thanks for attending. Happy to take any questions.
Thank you, Jorn. That was great. I think we've got a couple questions in chat, so I can go ahead and read them off for you. Let's see. First and foremost, PyMX equals PyMC underscore experimental. Isn't that target accept value of 0.98 a bit high? What is your R hat? RHAT?
Yeah, so I like the very technical detailed question. Yeah, so since this is a very heavy tailed distribution, the extreme value, I had to increase basically the target ratio. The R hat, they are, I don't know on top of my head. I'm happy to come back to you. We'll look it up and share that. But I checked those and they're in the expected range.
And we had a request for slides. Is there a place that we can view these slides?
Perfect. Yeah, I mean, I will basically haven't done it yet, but I will today add the slides to the GitHub. So there's a notebook that actually works through the entire thing we discussed today, and I will add these slides as well. And I will probably also post it on Discord.
Yeah, that would be fantastic. I'm just gonna include the link that you shared on your screen in chat. Great. There we go. Yeah, another request to get slides on Discord. Let's see.
Sure.
Got another question. Instead of using latitude and longitude for X, can we instead use the range from the Newark station to the surrounding stations?
Well, not really, because although in my talk I focused on like this one particular station, but when I code it up, I do them all together. So I need to have the distance between all the different stations, not only between Newark and the other stations.
Thank you. And last question we have time for from Christopher. Put it on stage. When do we need Gaussian process, and when does that have more value over nonlinear least square?
Well, so the Gaussian process here is that as I mentioned, I can use it as a prior. So think about it as sampling over functions. So yeah, I don't think there is an easy equivalent for a non-Bayesian way. But yeah, I mean, the Gaussian process is a very wide subject. I've only scratched tip of the iceberg and focusing on a very specific application.